Okay, let's start. Students who don't think about this class or talk about this class in their other classes, but they're also always talking about some other class in my class. Not that I'm actually bothered by that, but it's just my way of saying good morning. Just talking about chemistry all the time. Is your chemistry teacher more important than me? Continuing from last time. You guys had a test day?
We did.
Yeah, we did.
Yeah.
Like a test, like big exam.
Exam.
Like
Yeah.
test, is this 3? Okay, so continuing from last time, we are going to continue with the handout. I forgot those examples that I wrote on the board, I actually put in this handout in one section. So we're going to continue doing what we were doing last time. But we're also going to move on to a different kind of problem. Not that it's different, but it's going to be stated differently. As well as, so you should pay attention to the handout. There's a handout on curve sketching. It's on the class website. And so we're pretty much going to be working through that. But I wrote up some things that we want to pay attention to before we actually jump into this. And pretty much everything on this handout we've actually covered already, except point 3, which even here I put a little blurb explaining how to deal with point 3, but I guess I can talk about it, and that was finding asymptotes. So, an asymptote, essentially, this is a curve, a graph, approaches as the x or y coordinate. Approaches infinity. So that's the basic idea. So sometimes you have this sort of behavior where you might have a straight line or some other kind of curve, but you realize your curve gets closer and closer to that curve as one of your coordinates go to infinity. So for example, you're looking at the arctangent graph. The line on the arctangent graph, the line y equals pi over 2, is an asymptote. More specifically, it is called a horizontal asymptote because it is a horizontal line, and it's just the line that your graph will approach as your x-coordinate goes towards infinity. And you might have another situation looking at something like, so this is like y equals tan inverse, right, has a horizontal asymptote. You might look at something like y equals 1 over x minus 1, which has what we call a vertical asymptote. And notice that as you think of your y-coordinate going to infinity, at the point 1, you're approaching this vertical line. That's called a vertical asymptote. Right? Now there are many kinds of asymptotes. You have what's called oblique asymptotes, but we're not going to care. So there are many kinds. We only care about 2 kinds of asymptotes. These are the horizontal and vertical ones. More specifically, these are horizontal or vertical lines that a graph will approach as one of your coordinates are becoming infinite. So let's deal with one at a time. Let's talk about the horizontal ones. Asymptotes. Call it HA for now. So this means as your x-coordinate goes to either positive infinity or negative infinity, there is some horizontal line that your graph is approaching. A lot of times you want to figure out what that horizontal line is, and it turns out that intuitively you notice this, what they're kind of asking is, as your x is approaching infinity, are your y values approaching something? So we can pretty much talk about this purely in the language of limits. Okay. So, given some function y equals f of x, you're going to compute, in general you want to compute two limits, the limit as x approaches infinity of the function, and the limit as x approaches minus infinity of the function. Now if either of these give you a constant number, finite, that's the important part, has to be finite number, say L, then y equals L is a horizontal asymptote. Right? And that will be its equation. So you can imagine that in terms of the inverse tangent, if you take the limit as x approaches infinity of this function, the answer will be pi over 2. That means there's a line y equals pi over 2. It's not a part of the graph, but that's the line that your graph is approaching as your x-coordinate goes off to infinity. Similarly, if you find the limit as x approaches negative infinity, you'll realize y equals minus pi over 2 is the line that this graph is approaching as you move to the left. So in that sense, horizontal asymptotes, they tend to be a part of what you might call, not a part of finding what you might have termed in pre-calc as end behavior. I don't know if you've seen that phrase. Right? But you're pretty much determining how your graph behaves at the ends, at the far right or the far left. And in the event that you can take a limit and it approaches a finite number, it means that there is some horizontal line that your graph will approach as you move to the far right or the far left. One thing that does cause a little bit of confusion sometimes is a graph may cross its horizontal asymptote, right? And that shouldn't be considered strange, okay? So you might have a graph doing its thing, and maybe you find that this is a horizontal asymptote, and the graph might do something like this. It can cross its horizontal asymptote, and then eventually it's going to level off, right? But the fact that it will cross that horizontal asymptote one or several times shouldn't be strange to you. It's kind of strange to do this with vertical asymptotes. It can happen, but usually the nice functions that we do in Calc 1, like your rational functions or your trig functions or whatever, they tend not to touch their vertical asymptotes. It's not that it's not possible to do that, but the nice functions that we deal with rarely actually do that. So if you find that a function, if you're sketching a graph and you're crossing a vertical asymptote, that's kind of strange. You need to make sure that what you're doing is correct. However, passing a horizontal asymptote isn't strange at all. It's very common. Let's talk about the vertical asymptotes. Which I will call VA. So this is just a vertical line that a graph will approach as the y values are going to infinity. So, and this one, you can also define in terms of limits, but usually when you're actually figuring it out or computing something, you don't really think of it that way. But the definition is in terms of limits as well. We say x equals a is a VA of f of x if the limit as x approaches a from the right of f of x is infinite, or the limit as x approaches a from the left of f of x is infinite. So the example, y equals 1 over x, you'll notice that the limit as x approaches 0 from the right of 1 over x, that is going to give you positive infinity, while the limit as you approach x, as approach 0 from the left of 1 over x, that gives you negative infinity. You can therefore conclude that x equals 0 is a vertical asymptote. Now, some notes on vertical asymptotes. For functions we look at in Calc 1, it's strange for a function to cross its vertical asymptote. Not that it can't happen, it's very strange for the kinds of functions we look at for that to happen. And it's not correct to think of it this way, but in this class you can pretty much assume you're never going to cross the vertical asymptote. I'm never going to give you an example where the function crossed the vertical asymptote. So for this class you can kind of say, oh, it's never going to happen, but in general it can happen. It's just that you'd have to be a strange function. So a common scenario, especially in Calc 1, comes up when graphing rational functions. And so here is the scenario. I think I should put this in a different color. Because whenever you want to find the vertical asymptote for a rational function, you should be thinking of it this way. way to think about it, well, x equals k is the vertical asymptote. The quicker way to think about it for rational functions, which is usually where you're going to need to find them, is you're finding where the denominator is 0, and you just need to make sure that the numerator doesn't also cancel this. So, for example, if you're looking at the function 1 over x minus 1, then clearly x equals 1 is a vertical asymptote. X equals 1 makes the denominator 0, and the numerator has nothing that would cancel that from happening. And so that creates a vertical asymptote. If, on the other hand, I were to say, look at this function, then x equals 1 would not be a vertical asymptote here. Because what would happen, now simplifying does not fix the domain, but it can tell you when an asymptote does not occur. You can imagine that if I were to simplify this, this would be x minus 1 times x plus 1 over x minus 1, and there's something in the denominator that's going to cancel the problem. Now once that happens, it is no longer a vertical asymptote, it is what we call a hole. Okay. So that means whenever you can simplify the function to cancel a division by 0, it doesn't mean the problem of division by 0 goes away. It just means that it doesn't create an asymptote. So pretty much what this function is going to behave like x plus 1, except when x equals 1, it's going to have a hole. You'll have that being created. As opposed to this guy, which actually you stretched earlier, it creates an entire asymptote. So if you have a division by 0, and there's nothing to get rid of that division by 0, then that creates a vertical asymptote. You're going to have a vertical line that your graph will approach. And it necessarily means in this case that your graph cannot touch that vertical asymptote, because touching it means division by 0, which we know cannot happen. Okay? So if you have something that makes the denominator 0 and there's nothing to fix it, it's a vertical asymptote. If you have something that makes the denominator 0, but you notice that, oh, I could simplify to cancel a problem, it's not a vertical asymptote, it's a hole. Okay? And that's when it comes to rational functions, your ratio of polynomials, that's the easy way to think about it. So you're not necessarily going to think about it in the limit way, you're going to think about it in this way. Simplify, and anyone after simplifying where that will cause a division by 0, you're going to have an asymptote there. Anyone that gets cancelled in the denominator that upon simplifying, that would have caused a division by 0, but it seems like you can get rid of the problem, that creates a hole. So that's the easy way to think about it. Yeah, so that's the quick and dirty about vertical and horizontal asymptotes. These are the only ones we need to care about. So the horizontal asymptotes, compute the infinite limits. If you get a constant answer, y equals that answer is going to be your horizontal asymptote. Otherwise, there is none. For vertical asymptotes, the only situation where this is going to pop up is, for us in Calc 1, is with rational functions. And pretty much all you need to worry about here is division by 0. Division by 0 creates a vertical asymptote. And your graph can definitely never touch the vertical asymptote in that case, because division by 0 is nonsense. However, if you're in a situation where something in the numerator or elsewhere can kind of cancel that division by 0 problem, it creates what we call a hole. So it doesn't create something crazy that your function completely has to avoid, but still technically being there at the original function is nonsense because it would create a division by 0. So you have to say, oh, there's some problems going on here. Any questions so far? Any questions on chemistry? Let's continue. Yeah, so that's really the only new thing you need to know about to complete this next section. But other than that, in one sense, the problems that we're going to be doing now, they're kind of annoying, but in another sense, they are very simple. They're annoying in the sense that it'll usually take a long time, require a lot of calculations, but in terms of, there should be no question in your mind of what calculations you should be performing. So just like with related rates, there is a sequence of steps that you need to go through that you'll see on this handout, and you pretty much always go through these sequence of steps. And again, pretty much in this order. So ultimately, the way we kind of check whether you really understand what concavity means and what it means to find a local max or min is to go through a curve sketching exercise. Now, of course, in the real world, human beings don't sit around sketching curves. We have a computer do it, but it helps to show you understand the important idea of actually what these things would look like and how they would actually affect graphs. Which, as I said, that's the more important part. To be able to look at a graph and be able to understand what's going on and talk about the nuances, that's the point. But it's hard to test you on nuance, so instead we just test you on curve sketching. If you can properly sketch a curve and find all the relevant features, we'll know that you understand. Okay, so that's kind of the idea here. So when you're sketching a curve, you're pretty much going to go through these 6 steps, and pretty much these steps bring you through finding all the important features. So you see step 1 is to note the domain. Like yesterday we ran into that problem where we did the first derivative test and it looked like it was a maximum, but it turns out that 0 wasn't in the domain, so it was nothing. So that's what step 1 is about. Pretty much figuring out what inputs are you not allowed to be, right? So you should know what the domain is. Second of all, you should find the x and y intercepts. Where do you touch the horizontal and vertical axes? You need to make sure your graph is passing through those points. Then you would find the asymptotes, which is what we just went over. Okay? Now, those would be done as on paper, you'd represent these guys by broken lines. And so you just draw these broken lines. And by doing that, you're indicating this isn't a part of the graph per se, but it's meant to guide you when sketching. You need to know what you're avoiding or what you're approaching. Okay. Then you're going to find the intervals of increase, decreases, maximums, and minimums, and you should know what the first derivative helps you with that. Then you should know the intervals of concavity and finding inflection points, and you remember the second derivative helps you with that. And then ultimately you want to sketch the graph. So you're going to draw a picture of a graph that has all those features that you would have discovered between points 1 to 5. And this is called curve sketching. Okay? So on the second test and on the final, you will have one problem that's just about curve sketching. I'm going to tell you a curve, and I'm going to say, find all these things and draw the graph. Okay? So that'll be one problem. And sometimes it might be annoying, but at the same time, you know what steps you should go through. Just get good at all these steps and go through them, and everything should be fine. To that extent, to that end, I probably want to actually, so these were the examples I wrote on the board that we were going to do last time. They're kind of the easier ones, and the point of those was to test you on what I taught you yesterday. But when it comes to like an exam, like the test or the final, I'll probably ask you a question like, what's down here? So this is probably, if you want to practice for the exam, you more want to focus on these types here. Like, I mean, in Calc 1, I'm not going to ask you to graph a polynomial, because technically you should know how to do that since pre-calc. I wanted you to practice graphing, especially rational functions, because those are a little bit more complicated. Now, whenever I ask you to graph those, the problem will be stated pretty much exactly as you see here. So it's going to say all this stuff. So it's going to say, consider the given function. The first derivative and the second derivative are given, and you don't need to verify them. So normally when I give you a problem like this, you're not going to need to differentiate. I'm going to tell you the derivatives, right? Because earlier in that test, I would have tested you on whether or not you can find a derivative. So I don't want to test you on that again, right? So I'm just going to give the derivatives to you. It's just important for me to know that you know how to use a derivative or what it means to be a derivative, okay? So I'll say, okay, here's a function. The formulas for the first and second derivative are given, you don't need to verify them. And I'll usually ask you about the domain as well. So I'd say something like, find the domain, the intercepts, asymptotes, relative extrema, intervals of increase, decrease, and intervals of concavity, inflection points, if they exist, and then use this information to graph the function. Indicate on your graph all these features. Right? That's going to be a question, like for sure. So that statement is going to be a problem on your second test and the final. The only difference is the particular function that I asked you about is going to be different, but that's how I'm going to ask you, exactly this way. Okay? So I probably want to jump ahead and do maybe one or two of these examples, and if the mood strikes or if there's some that we don't understand, I might go back and do some of these. But probably let's just jump to one of these to see how it would actually be done. So in the second set of examples, the more examples with additional info given, let's actually do part A. Okay? So here you're given the function, and you're given the derivatives, and you're going to use that information to find all these features and sketch the graph. Let's actually jump into that. And pretty much all the principles we're going through here would have been the ones that I went through if we continued with the last class examples. But let's actually do. Oh, by the way, I do mention some footnotes when going through this handout that you guys should be reading, because I mentioned, some common mistakes students would make and etc., some other stuff. But really, as long as you avoid those mistakes and know these 6 steps, you should be fine. So let's do more examples. Let's talk about A. So our function is, looking at the function x squared over x squared minus 4, we're told that the first derivative is minus 8x over x squared minus 4 squared. We're told that the second derivative is 8 times 3x squared plus 4 over x squared minus 4 cubed. So let's go through the motions. We're going to go through those 6 things. Pretty much in order. So 1, domain. What is the domain of this function? Oh. What's the domain?
X can't be plus or minus 2.
X can be plus or minus 2, right? That's it. So you write down this. That's your domain. Because you have denominator equals 0. That's where rational functions don't work. Now, intercepts is the next thing you look for. So let's find the x-intercepts. To find those, what do? Set y equals 0, solve for x. So you have 0 for x squared minus 4. This means that x equals 0 is your x-intercept. Find the y-intercept. You set x equals 0, solve for y. This means you get y also equals 0. So that tells you the intercepts happen at the origin. So not a big deal. We're just pretty much going through the motions. 2 out of 6 steps down, 3. Next, we're going to want to talk about the asymptotes. So let's look at the horizontal. How do you find the horizontal? Or you find the infinite limits of the function. Rational functions are nice because it turns out that the limits Whether you go to the positive or negative, they're actually going to be the same answer. So once you find one, you automatically find the other. What's the limit as x approaches infinity of this function?
Infinity.
No,
No, 0.
no.
One.
Oh, sorry, 1.
It's one. It's pretty,
Yeah,
it's
yeah.
pretty much the
Yeah,
third case
yeah,
that
yeah.
you didn't pick.
Yeah.
Okay, the top and bottom powers are the same. The highest power and the top and bottom are the same, so it goes to the ratio of coefficients. It's 1. So that means y equals 1 is your horizontal asymptote. Vertical asymptote. So for the vertical asymptote, I need to find where's the denominator 0, and this doesn't get cancelled. So pretty much I'm going to say set x squared minus 4 equals 0. This means x equals plus or minus 2, and there's nothing to cancel it. So that's pretty much it. X equals minus 2 and x equals 2 are vertical asymptotes. Horizontal asymptotes. Okay, and so those are the asymptotes. The fourth thing we're going to want to find is the stuff we can find from the first derivative. So the fourth thing is going to be increasing, decreasing, maximums, minimums. Okay. And you should realize that what tells you about that is the first derivative. So you're going to ignore the original function for a second, and you're now going to focus on that guy. You'll immediately notice, or should immediately notice, that the critical points are x equals 0, x equals minus 2, x equals positive 2. This is where that function is 0 or undefined. So you're going to draw a number line. You're going to plot those points on that number line. You're going to test them in the first derivative. So you're going to pick some random points, maybe a 3, maybe a minus 1, maybe a 1, maybe a 3, and you're going to plug them into the first derivative. Now, sometimes you'll be able to use some tricks to your advantage here. One, you will notice that you only care about the sign. You don't care about the actual values. So looking here, you'd realize that the denominator has a square on it. So as long as the denominator is not 0, it's always going to contribute a positive sign. So when you're plugging in these numbers, you can realize, I only really care about what the top is doing, because the bottom is a square. It's always going to give me a positive sign. So just looking at the top, that's minus 8x. If I plug in a minus 3, that will give me a positive number. If I plug in a minus 1, that will give me a positive number. If I plug in a positive 1, that will give me a negative number. If I plug in a positive 3, that will give me a negative number. So I have a function that's doing this: increasing, increasing, decreasing, decreasing. Now you can ask yourself, can we identify any maximums and minimums on this chart? Okay. Do we have a max or a min on this chart?
Max.
Where?
0.
So 0 seems to be a maximum because you're increasing then decreasing, so at 0 you must have hit a peak. Double check with step 1. Okay, 0 is a valid point, so yeah, that's definitely a max. So now we can start to, and you can notice, now let's find this location, right? So you're going to find the location of the maximum. Now if we're looking for a location, what are we looking at?
Original function.
The original function. So now I know that there's a max, it happens at 0. If I want to find a specific location, I'm going to look at the original function and evaluate that at 0, which of course is going to give me 0. And now I'm able to write down the answer to the fourth section. So it's increasing, where is it decreasing, where are there maximums, where are there minimums. So realize it's increasing on these two intervals. So from minus infinity to minus 2, union minus 2 to 0. It is decreasing on these two intervals, 0 to 2, union 2 to infinity. it has a maximum at 0, 0, so that's a point. Right, so these are intervals here, not coordinates. The notation looks the same. And minimums, we have none. And that is your answer to the fourth section. Then you move on to the fifth set of things you want to talk about, concavity. And of course, inflections. Either way, you should be looking at the second derivative. Okay? So the second derivative is 8 times 3x squared plus 4 over x squared minus 4 cubed. Find the critical points of that. That's going to be x equals plus or minus 2. Okay? So that's never 0 because the numerator is never 0. The numerator is always a positive number. So the denominator equals 0 is where the critical points are going to happen. That's where your function is undefined. This happens at plus or minus 2. You are going to plot the number line. You are going to test values in the second derivative because you're looking for concavity and inflections. So you're going to plot minus 2, you're going to plot positive 2. Then you're going to test numbers. So say let's test the minus 3, test the 0, test the 3. So now, if I plug in a minus 3, again I can use a trick here. Notice that the numerator is actually always positive because it's a square plus some positive numbers. So the top is always positive, so really I'm only checking the denominator here. If I plug in a 3 or plus or minus 3 here, it gets squared and becomes a 9, you subtract 4, that's positive. So it's going to be positive over here, positive over here. If I plug in a 0 on the other hand, I get 0 minus 4, that's going to be negative. So what does a positive mean here?
Concave up.
Concave up like a cup. Up like a cup. Negative means concave down, down like a frown. So this is not talking about increasing or decreasing, it's talking about the shape of the graph. Any inflection points here? Well, here we switch from concave up to concave down, then we switch from concave down to concave up. So it seems like 2 or minus 2 might be inflections, but then you remember, not in the domain, so they are nothing, right? So there are no inflections here. So now you can summarize this guy. And you can say it's concave up. Where is it concave down? Where are there inflections? So it's concave up on minus infinity to minus 2, union 2 to infinity. It is concave down from minus 2 to 2. And it has no inflection points. That's the answer to the next set of questions. Now this basically says, okay, we found, this is all the information you need to find. So now that you've found all the information, let's sketch the graph. What would it look like? So now we're going to sketch this graph. It's supposed to be a vertical line. And that's supposed to be a horizontal line. But I'm only human. So here's the x-axis, here's the y-axis. And let me kind of tell you how I do it. I think this is probably the best way. So first, how I got this was I'm first going to plot intercepts. Maximums, minimums, inflection points. So I'm first going to go through and I'm going to plot all the important points on this graph. Okay? So we found that the intercept was the origin. So there's that. And this is also a maximum. There were no minimums, there were no inflection points, there were no other intercepts. So in terms of coordinates, points that I can plot, that's all of the important ones. The next thing I always worry about is the asymptotes. So I'm going to go over here and I'm going to put in the horizontal and vertical asymptotes. The horizontal one was at 1, if I recall. Right. So you're just going to draw a broken horizontal line passing through 1. Then we had vertical asymptotes at plus or minus 2. So these are points that the graph cannot touch. So minus 2, that'll happen. And at positive 2, that'll happen. So the asymptotes are usually the things I like plotting in a second. So here I'm trying to figure out the skeleton of my graph, right? What are the important points I have to go through? What are the lines I have to avoid? What are the lines I have to approach? I kind of start to map it out that way. So now the next thing, I'm going to start charting my intervals. Of increase, decrease. Then I'm going to chart the intervals of concavity. Okay. And usually, because we went through a lot of calculations, if you're doing this all on one page, everything that we did, you'll realize that there are tons of numbers out there. So I like to put all the information that in those calculations on the picture that I'm graphing. So I would normally go something like, so let's do the increasing. I know from negative infinity to minus 2. So what I do is that way at the bottom of the graph, I kind of put this little thing that tells me, okay, from here back, it's increasing. And I know from here, between here and here, it is also increasing. So I'll write a little chart like that at the bottom. Right? So it's not a part of the graph, it's just something to help me. Then I'll look at decreasing between 0 and 2 and 2 to infinity. So I'll write a little thing here. I know that's decreasing, and then I'm decreasing all the way back. Now let's look at concavity. Up to minus 2, and after 2, we are concave up. So from here back, I know I'm concave up. From here forwards, I am concave up. And everywhere in between, I'm concave down. So I'll just chart this here. Now write concave down. And now what you'll see is before I even started drawing the graph, all the information that I just found is now summarized on the picture, on the axes, right? So at this point, I should be able to start graphing without really having to look back and forth between the calculations because everything is here. So now let's actually start drawing the graph. Notice here, I am increasing. Over here, I am decreasing, and I know that it's a maximum. So I know I have to be looking like this, and I know that my graph should be going down. I also know it will never cross this vertical asymptote, but I'm going to just head towards it. So my graph is going to look like this. Then I double check, make sure I'm shaped correctly. I should be concave down in this whole region, so I should be shaped like a frown the entire time, right? Like at this point, that's going to be important. So if you just draw like a straight line, or you draw things bending this way, I'll know that you don't know what concavity means, right? It has to look like a frown, okay? Because it's concave down in this entire region. Over here, it's concave down and increasing. Over here, it's concave down and decreasing. So it's moving up as you go from left to right with a frowny face shape. Now it's moving down as you go from left to right with a frowny face shape. Okay? So that's what the picture looks like over there. Now, You can test coordinates here, but you can also just think about the important concepts. One is to notice that the graph could not be down here. Why do I know it cannot be down there? Because I should be increasing. I also know that I have to avoid this red line and I will have to go up to infinity. Now if I'm increasing from down here and go up here, how does that contradict what I've been doing? Does anyone notice how it contradicts?
The horizontal asymptote.
Again, crossing a
you
horizontal
go through-
asymptote isn't strange, that's not the problem. Crossing the x-axis is the problem. If I started down here and increased, I would cross the x-axis. But what would that mean? That means that's an x-intercept. But I already found all the x-intercepts. There's only that one. So the graph can never be down here, it has to be up here. Now you can say, oh, well, is it here? And then I should go up. Then you'd worry about crossing this horizontal asymptote. Now in general, that's not bad, but I would check if it crosses the horizontal asymptote. Is there a situation where this function equals 1? So I'm checking, does it cross the horizontal asymptote? Is the output ever y equals 1? And of course you'd realize that would mean that your x squared is equal to your x squared minus 4, which means, of course, that 0 would be equal to minus 4, which is completely absurd. So in this case, I know it doesn't cross the horizontal asymptote. So I also can't be here. It means I must be up here, right? So you could also figure that out by plugging in a number. You'd realize you always get numbers bigger than 1. But you can also just think about the concept and just know, I can't be down here because that would create an x-intercept. I can't be down here because that would cross my horizontal asymptote, and I know I just checked that that never happens. So my graph has to be up here. So I have to be increasing going towards that vertical asymptote. I am concave up, shaped like a smiley face. And because I'm increasing the whole time, now I'm going to be going down along that guy. Right? Now I'm never going to touch that blue line because the output is never 1. Similarly, over here, if I have to be decreasing, I can't be down here because that will create an x-intercept. Can't be up here because that will be across the horizontal. I must be at the very top, and you will consequently get a graph like that. So this graph has that picture. It looks like this, and then there's a little hill in there. And there are asymptotes. It doesn't touch the vertical, and it happens to not touch the horizontal in this case. So practice the rest for Monday. If you want to check your work, you can check in Wolfram Alpha or something like that. Just ask it to graph it, and you can see, check if you're correct. But practice going through, finding all those important features, because that's important. That's definitely something I'm going to test you on. Yes, we'll stop there.